All right, guys, I'm super excited. Today we are getting into the beginnings of what is going to make up the entire second half of our year. You may notice a new symbol here. This is the integral symbol. And the way we read it is we read this as the integral of f of x from a to b. So the bottom part is where it begins and the top part is where it ends. Sometimes we'll say the integral from a to b of f of x. This dx at the end of it just denotes where the integral ends. We don't really say it out loud a lot of times. So we say the integral of f of x from a to b. This becomes more important in a multivariable calculus course, which would be like your third or fourth semester of calculus. When there's multiple variables, it becomes important, like what this is. But for the first year, this is just the end of the integral. You'll see it always, but it won't be something you need to deal with. And what the integral represents is the signed area, and I'll explain this in a second, bounded by x equals a, x equals b, f of x, and the x-axis. So real quickly, if we have, f of x, and we want to do, if this is f of x, then the integral from a to b of f of x is the signed area between x equals a, x equals b, the x-axis, and the function f. And what you'll see is that sometimes x and these lines make area above the x-axis, and this is going to be positive. Area is always positive, but when we talk about signed area, we talk about whether it's above or below the x-axis. This is going to be negative. So, sorry about that. So any area that's above the x-axis we'll consider positive signed area, and any area that is below the x-axis will be negative signed area. So, calculus is going to help us address a fundamental problem that they couldn't solve for like thousands of years, which is how can you find area under curves? We knew how to find area of triangles and rectangles and circles, and putting those things together gave us a lot of power, as you're going to see today. But over the next few weeks, we're going to develop a way to find the area of any function, and it's going to be very nice. So let's look. Today, our first focus is going to be using geometric techniques to evaluate these integrals. So how do we say this out loud? What should we say for this? This is the integral from 1 to 3 of 4. And we could put y equals 4. We could consider this like a graph. So this is asking us, what is the area between x equals 1 and x equals 3? So that's right here. So x equals 1 and x equals 3 of the line y equals 4. So if we graph the line y equals 4, we'll be able to answer this question. Y equals 4 is this. This is y equals 4. Here's x equals 1, x equals 3. And we're doing the signed area between f of x, the x-axis, and x equals 1 and x equals 3. Oh, something's wrong, guys. Oh, this is so terrible. This is not y equals 4. I did not count up high enough. This is 1, 2, 3. So let's go up higher. Sorry about that. This is y equals 4. This is not what we wanted. And so we want the area between y equals 4, the x-axis, and these two. And so if we shade this in, this is the area we're talking about. Now, how do we find the area that's here? Well, we use our geometry. This is a rectangle, and we know that for a rectangle, the area equals the length times the width. So I see 2 times 1, 2, 3, 4. So 2 times 4 is equal to 8. This integral is 8. And, soon we'll be learning about what's going on. We can use a calculator to visualize this a lot of times. If I put y equals 4, let's go between, okay, cool, that's good enough. And I press, there's a calculate button. If I do the integral, so here's y equals 4, and I do the integral from 1 to 3, you can see there is that area, and it's 8. The integral of f of x from 1 to 3 is 8. And we can see a nice pretty picture there. Okay, I want you guys to try this next one on your own. It's a little bit different, and you're going to have to think about it slightly differently, but I think you can do it. What is the area, the integral from 0 to 3 of x plus 2, and what is that area? What is that area it's asking for? What numerically is it? So hopefully you graphed y equals x plus 2. So it has a slope of 1 and a y-intercept of 2. So a y-intercept of 2 and a slope of 1. This is y equals x plus 2. And we're doing the integral from x equals 0 to x equals 3. And this time we do not have a rectangle. So this area is going to be a little harder to find. We have two options. We could break it up into a rectangle and a triangle. Or, and this is going to be really useful, guys, we can think of this as a trapezoid. And we are going to need this in a couple of days. So now is as good a time as any to make sure we know how to find the area of a trapezoid. If you have a trapezoid, and a trapezoid, of course, has two parallel bases. These are parallel to each other. This is called the first base, and this is the second base. Then, and you have a right angle here, or you could have the height, but we're always going to have a right angle in calculus. So, because it'll end up looking like this, right? So the way you find the area of a trapezoid is you take the average of the two bases and divide by 2. So you average these two together, and then you multiply that by the height. So it's kind of like length times width for a rectangle, except you have to like find the average. It actually ends up making it be like, turns it into a rectangle when you make this average. There's some geometry behind that there. So let's use that here. Base 1, here's base 1 is 2. This other parallel side to it is 1, 2, 3, 4, 5. We can average that together. So 5 plus 2 divided by 2. That's the average of the two bases divided by 2 times the height. So the height is the distance between the two bases, and that is 1, 2, 3. So we get 7 halves times 3. Whole numbers always just multiply on top of the answer, and so it's 21 halves, or 10.5. 10.5, 21 halves, doesn't matter what's going on. And you would have gotten that same answer if you had found the area of this rectangle plus the area of this triangle. The area of the rectangle is 6, the area of the triangle is 4.5, and you would have added it together to get 10.5. And that's a fine way to do it as well. Okay. This might look a little bit harder if you don't recognize it. This is saying find the area between x equals -2 and 2 of this graph, this function. Well, what is this function? And hopefully we recognize it from Algebra 2 and pre-calculus, but maybe we don't. Remember in Algebra 2 we learned about x squared plus y squared equals r squared. This is the equation of a circle. And you can get the equation of a semicircle. So like, for instance, this is coming from the circle x squared plus y squared equals 4, where this is the radius is 2. So 2 squared is 4. So it's a circle with a radius of 2. And you can always solve for y by moving the x squared to the other side and then taking the square root. And when you take the square root, it's supposed to be positive or negative to do the top half of the circle and the bottom half of the circle. But if you only have 1/2, it's a semicircle. So this is a semicircle centered at x equals 0 with a radius, this is the radius squared, of 2. And so this actually looks like this. So it's a semicircle. And we should be able to find the area of the semicircle. What is the area of this semicircle? Well, I hope we know that the area of a circle is pi r squared. And so if you have a semicircle, you just take the area of the whole circle and then divide that answer by 2, and that'll be half of the circle. So in this case, r is the radius is 2, so it's pi times 2 squared divided by 2, which is 4 pi divided by 2 is 2 pi. So 2 pi is the area of this semicircle. We did pi r squared, the area of what the whole circle would be, dividing it by 2 because it's only half of a circle. If it was a quarter of a circle, we would do pi r squared divided by 4. Okay, I want you guys to try this last one on your own, and I want you to be very careful to remember that the integral is the signed area. So what is the integral from -3 to 3 of 2/3 x? And what you should have done is you should have graphed 2/3 x. It has a y-intercept of 0 and a slope of 2/3, so up by 2, over by 3. And when we go down to the left, it goes down by 2, left by 3. And we're doing the integral from -3, so that's when x is -3, to when x is 3. And it's the signed area. So we got to be a little bit careful here because this area here is positive, but the area between x equals -3, f of x, and the x-axis, this is below the x-axis. So this is negative area. It's going to be negative area is how we're going to think of it. And you can see right away that these are actually the same as each other. So you've got like negative something plus something, and that's 0. This integral will be 0. But if you really wanted to calculate it, you could find the area of each of these triangles. And the area of a triangle is equal to 1/2 the base times the height. And for both of these triangles, that comes out to be 6 divided by 2, which is 3. So this one's +3, this one's -3, and when you add them together, you get 0. So remember, an integral is the signed area. If this had been the bottom half of the semicircle, it would have been a negative, right? If anything is below the x-axis, it's a negative. Okay, there are 2 special integral properties we want to know. And the first one is kind of obvious, okay? So it says like, hey, you've got a function, right? And you go from A to A. How much area is this? And the answer is, it's basically, you can think of it like a rectangle with a height of f of A, so a height of f of A, but a width of 0. So it's f of A times 0. And so this always has an area of 0. If you go from the same thing to the same thing, well, you're not going anywhere, and so there's no area, and so the area will be 0. So if you go from A to the same number, it will be 0. The other really important one is if you're going from B to A, and we'll talk about this more later this year, why this is the case. So this is definitional, and this will come up a lot of times. You want to make sure you feel comfortable with this. The integral from B to A is the same as the negative of the integral from A to B. So you can reverse the order you go in. So if you ever go from if it asks you for the integral from right to left, it's going to be the negative of, we always go from, so it's always supposed to be the integral from left to right. And if it, for some reason, is backwards and it gives you from right to left, then you always say it's going to be equal to negative the integral from left to right, and then you actually find that area. So you have to be careful that it's actually going from left to right. So if this had said the integral from 3 to 1 of 4, we would first start by switching it around to being negative of the integral from 1 to 3. All right, let's try this and see how you do. What is the integral from pi to pi of tangent of theta d theta? Again, this d theta is always going to go with the variable, and you don't need to worry too much about it. This integral, hopefully we found, is 0 because the limits of the integral are the same, so there's not going to be any area. Okay, how about this next one? And I'd like to point out, you really want to use your answer from number 3 when we got 10.5 or 21/2. So the integral from 3 to 0, well, here's 3, here's 0. That's going from right to left. So going from 3 to 0 is right to left. Hopefully you found that this is negative of the integral from 0 to 3 of x plus 2 dx. So we already found the area from 0 to 3 of x plus 2. That was right here. That area was 10.5. And so this is the negative of that area, negative 10.5. Okay. You don't have to redo an integral. If you've already done an integral, like you found that area, great. Just make it negative. Another property of integrals, and this should make sense, is that if we have a, c, b, then the integral from a to c is going to be this, and the integral from c to b is going to be this. And so what is the integral from a to c plus the integral from c to b? Well, it's the integral from a to b. It's basically saying like you can split up areas from left to right. You're saying if you go from a to c and you go from c to b, that's the same as going all the way from a to b. So if you have integrals that get split up, it's just the integral from a to b. And it's useful in both directions. So let's see how we do on this. Now, this is a common setup on the AP exam where they give you some integrals and then you have to use integral properties to rearrange it. It's not particularly hard once you get good at it. So it tells us the integral from negative 2 to 3 of f of x. And I'm going to draw a picture here. So it's when x is negative 2 to when x is 3. That integral of f of x, so whatever, is 7. So this whole area is 7. That's what it's telling us. And it tells us the integral from 1 to 3, this area is 4. So the integral from 1 to 3 of f of x is 4. The integral from negative 2 to 3 of f of x is 7. We'll be able to answer a lot of questions about that. What is the integral from 3 to 1 of f of x? Go ahead and try that on your own. And hopefully we recognize this is going backwards. It's going from biggest to smallest, so we need to make it go the other way. The integral from 1 to 3 of f of x, but it's going to be negative. And the integral from 1 to 3 was 4. It told us that right here. So this is negative 4. How about the integral from negative 2 to 1? What is the integral from negative 2 to 1? What is this area here going to be? Try to figure it out. Hopefully, you were able to figure out that since the whole area from negative 2 to 3 was 7, and the area from 1 to 3 was 4, then this part must be 3, because the integral from negative 2 to 1 plus the integral from 1 to 3 has to equal the integral of the whole way, from negative 2 to 3. So 4 plus something needed to equal 7. So this part needed to be 3, and so that's the answer. So it's just using some reasoning and some geometry to make sense of what's going on there. What about the integral from 1 to negative 2 of f of x? Well, hopefully we see this as backwards. It's going the wrong way. It needs to go from smallest to biggest. So the integral from negative 2 to 1 of f of x dx. But we need to make it negative, and we already found that. That was negative of 3. Okay. Great. Let's look at some more properties of integrals. If you ever have a constant times an integral, you can just pull the constant outside of the integral. So the integral of a constant times a function is going to be the same as the constant times the integral of that function. And this should make sense from Algebra 2. We learned about how when you have a constant multiplier times a function, what it does is it vertically stretches it. And so it makes the area inside that many times bigger as it would be. So you can pull that outside. Another useful property of integrals is just like when we were doing derivatives, if you have a sum or difference of two functions, you can split it up into two separate integrals and do them each individually. So let's see how we do. There's some function. We don't know what it is, but we know that the integral from 2 to 5 of that function, that area, is equal to 5. And the integral from 2 to 5 of some other function, maybe it looks like this. This is g of x. That area is -3. So use that to answer these questions. What is the integral from 2 to 5 of 4 times f of x? And I really hope, I bet you got the right answer, but I really hope you brought the 4 outside of the integral. It's 4 times the integral from 2 to 5 of f of x. And I hope you didn't skip straight to writing the right answer. I hope you saw that you could pull the 4 on the outside. And the integral from 2 to 5 of f of x was 5. So this is 4 times 5, which is 20. Make sure you're actually using the properties here. The integral from 2 to 5 of f of x plus g of x, hopefully we recognize that we can split this up into f of x, the integral of f of x plus the integral of g of x. And I would bet that even if you didn't do this, you got the right answer of 5 plus -3, which is 2. Okay. But I think we're going to see here that if you aren't using the principal properties, a lot of you are going to get this next one wrong. So let's see. What is the integral from 2 to 5 of f of x plus 3? Well, let's use our limit properties and split it up. The integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 3. Okay, the integral from 2 to 5 of f of x, it told us, was 5. Plus the integral from 2 to 5 of 3, what is that? Well, now you have to reach back to what we did earlier today. It didn't tell us what the integral from 2 to 5 of 3 was, but this is a geometry one that you can do using geometry. This is, what's the area of y equals 3 from 2 to 5? And so that area is going to have the distance between 5 and 2 is 3. The height is 3. So this area is, the area of a rectangle is 3 times 3, which is 9. So this area is 9. And I bet a lot of you put that the answer was 8 here instead of 14. So like I said, you want to be very careful that you're actually using the properties and you're not just being like, oh, this one is 5. Like, I bet a lot of you looked at this and you're like, oh, it's 4 times 5. Cool, 20. And a lot of you looked at this and you're like, oh, it's 5 plus -3 is 2. And then a lot of you looked at this one, and I suspect strongly that a lot of you put, oh, it's 5 plus 3, 8. No. Use the properties, stop yourself from getting it wrong when it actually gets more difficult, split it up, and then think how you can find that integral. This one was given to us. This one we needed to calculate. Okay, so be careful there. I suspect, hopefully, if you're being a little bit more careful now you'll be able to get this one correct. So the integral from 2 to 5 of f of x plus x, you need to split it up into the integral from 2 to 5 of f of x plus the integral from 2 to 5 of x. We should be writing dx at the end of our integrals each time, but if you don't, it will usually be okay, although every once in a while it can lead to a problem. Notice if this plus x had been on the outside, it wouldn't be part of the integral, but because it's inside the dx, that's one of the ways that it tells us it's part of the integral. The dx tells us where the integral ends. So the integral from 2 to 5 of f of x is 5. And the integral from 2 to 5 of x, we are not given that one. We need to do it geometrically. The line y equals x looks like this. And we're going from 2 to 5. So what's the y value here? Well, it's when x is 2, y is also 2 because it's y equals x. When x is 5, y will also be 5 because it's y equals x. So 5, 5. So we can find the area of this. Again, you can split it up into a rectangle and a triangle, but I strongly recommend learning how to find the area of a trapezoid when there are 2 parallel bases and a height. So the height here is obviously 3, and the parallel bases are 2 and 5. So we add 2 and 5 together and divide by 2, and we multiply that times the height. So this is the average of the 2 bases, 2 and 5. So this is 7 halves times 3, which is 21 halves, which is 10.5. So plus 10.5 is 15.5. Or if you wanted to keep it as a fraction, you could have put it as 31 halves. That's also fine. Okay, guys, so using these properties of integrals, like sometimes it looks really easy, and it is. Sometimes you have to be a little bit careful and actually use the property. What is the integral from 5 to 2 of f of x? Hopefully we noticed that this is backwards. It's negative the integral from 2 to 5 of f of x. And the integral from 2 to 5, it told us was 5. So the negative of that is negative 5. Hopefully we feel good about this. Okay, the last thing we're going to talk about is this is an indefinite integral. It doesn't have anything at the beginning or the end, and we will talk soon about what this means. This is a definite integral. It means what is the area between the x-axis and this function, although this one is backwards, so we would need to rewrite it as the integral from the negative of the integral from 1 to 3 of 4 minus x, and then you would just graph 4 minus x. Okay, guys, hopefully you're feeling good about this. You'll get lots of practice today on in your homework on how to do this. I think most of them you won't find too difficult. I hope I'm giving you a lot of time to practice this, because this is something that is going to be fundamental to our basis for what we're doing for the rest of the year, which is how do we find areas. And later we'll get to be able to find areas of curved lines. But for now, it's just like, okay, you know how to find the area of a semicircle. You know how to find the area of a triangle. You know how to find the area of a rectangle. And you know how to find the area of a trapezoid. And that's it. That's what you're going to be doing. So good luck today. Let me know if you have any questions.